Hello, ladies and gentlemen. Sorry. We're going to now talk about nested quantifiers and why we might need a nested quantifier. Okay, so just like we needed quantifiers to say some things in the English statement, in the English language, we also now have to possibly nest them to make new statements. So our statements can get more complex. So we want to say the statement, every real number has an inverse. If we recall in mathematics to have an inverse, if I add any two real numbers together, if they are inverses, then their sum is 0. Okay? And so this statement here represents this here. For all x, there exists a y such that x plus y is equal to 0, where x and y are real numbers. Okay? So that means that for all x's, there is at least a y. Okay, that when I add these values together, I get 0. So for instance, let's say for 2, the y that exists happens to be, so if x is equal to 2, the y that exists happens to be negative 2. So for any x I choose, there will be a corresponding y that will make this statement true. So we can also think of it as a nested loop. Okay? And not just what we have listed there, but if we do for all x there exists a y, we can think of it as for all x q of x, where q of x is now this new statement, there exists a y p of x y. Okay, so this is our two variable predicate, okay, where p of x y is this here. But instead of doing that full loop of keep doing that, we just do the nest. Because you guys are computer scientists, most of you, okay, we can think of it as that loop again. Okay, so if we think of the statement for all x, for all y p of x, y, that means that any pair of x and y must hold. Okay, so if I go through the loops of the y's, okay, I must find an x, a pair of x that will do it. And any one I choose, any pairs should work for my statement. If I get to a particular y and cannot find an x, or I get to an x and cannot find a y, then we see the statement will become false because the loop would terminate. Okay? And so if we have for all x there exists a y, okay, we want to find at least one y. So once I find that y, I'm good. So for every x, there needs to be at least a y. Doesn't have to work for all pairs, but at least one. Okay? If I don't find that y, then my loop fails. Okay. Now keep in mind, again, we might have infinite loops within our numbers, but assuming that there is a y out there and will make the statement true, my loop will continue. So let's look at the order of quantifiers. Sometimes we have to be concerned about the order of the quantifiers, okay, to see if the statement is going to be a true statement. So if p of x, y is the statement x plus y is equal to y plus x, and u is all real numbers, okay, then the statement for all x, for all y p of x, y, and for all y for all x have the same truth value. Let's talk about the truth value of that statement. The truth value of this statement would be true. And why is it true? Sorry, my handwriting is horrible. Because this is what we call the commutative law for addition. It's kind of x plus y is equal to y plus x. So any combination, it doesn't matter the order I choose it in, these values will be true. Okay. But let's think about this statement here. Q of x is equal to x plus y is equal to 0. If we write for all x, for all x, there exists a y q of x. Let's talk about the truth value of this statement. That means that for all x, any x I choose, there is a y such that this will make it equal 0. Okay. Now this statement, is that going to be a true statement or a false statement? So the way this is written now, this is a true statement. Why is this a true statement? Okay. For all x, any x I choose, let's choose x to be 3. Okay. The y, there exists a y, say negative 3, that when I add the sum, I get 0. But if I look at the order and change my order, so this time I look up there exists a y for all x. So this says there exists a y. Let's choose a y. Let's choose a y3. Okay, that for all x, that means that any x I choose, okay, it will equal 0. And that's not a true statement. There is only one x, which happens to be -3, that will make it be 0. So again, let's think about this. For all x, there exists a y is true. Right? It is true because for any x, there is a y, but there exists a y such that for all x means that there must be a y that any x I choose, any x, okay, will make this a true statement. And so therefore this statement is false. So the order of the quantifiers will matter based on what we're talking about. So for the next two examples, I actually would like for you to pause and try to go through and figure out the truth values of these examples. Okay. Now I will go through them after you've completed them. So let's revisit to see what you have. Okay. So if u is all real numbers and p of x is defined as x times y is equal to 0, what would the truth value of for all x for all y be? Okay, and so what would this mean? That means for all x, okay, that every single y I choose, any y I choose, that it would equal 0. Okay, if I choose x to be 2, okay, then I can choose y to be 4, and we see we have a pair that will make this false. So this full statement is false. Now let's look at 2. For all x, there exists a y. Okay. Is this a true or false statement? For all x, let's say x is equal to 2, there is a y. That y happens to be 0. That will make this true. So any x I choose, the particular existence of a y is equal to 0. So this statement is true. This next one, there exists an x that for all y. Okay. So there exists an x, let's say x is equal to 0. So there exists x that any y I choose, y can be any number. Okay? When I multiply these two, this statement will hold. Okay? So this statement is true, okay? Because there exists one. Okay? So keep in mind for 2, the y that exists must be 0. And for 3, the x that exists must be 0 also. Our last one, there exists an x, there exists a y. Okay, let's just choose one. There exists an x. Let's let x equal 4. There exists a y, it happens to be 0. Or vice versa, there exists an x equals 0 and y could be 7. It doesn't matter. But because there is at least one, we know in one of these cases, one of the two would have to be 0. But since that exists, this statement, will be true. So here are your solutions for this slide. Now let's look at this example here. Well, u is still our real numbers, okay? And p of xy is x divided by y is equal to 1. Okay? So for all x, for all y, p of xy, so this means any x I choose, x is equal to 2, that any y I choose, y is equal to 4, should hold. And does this hold? Of course, 2 divided by 4 does not equal 1. So this statement is false. So keep in mind, it must be any pair will have to work. But let's look at our next example. For all x, there exists a y. Right? So for all x, if I write x is equal to 2, then what y would I need to choose? Let's choose y is equal to 2. Then this statement will work, right? If I choose -1, then the appropriate y would be -1 for x. And then our appropriate y would be -1. Okay, let's put this circle so you know it's not minus that. Okay, then it grows. Is there any value that won't work if we're talking about real numbers? We got to think closely. So this appears to be true, but let's let x equal 0. Okay, what is the y that when I divide by another value, I get 1? Okay, can't be 0 because anything divided by 0 is undefined. So in actuality, you have to be careful. This one value for x violates the rule. So this statement is actually false. Let's look at our next one. Okay. There exists an X that for all Y. All right. So there exists an X. Let's choose any X that for all Y. If I choose X to be 1, then every Y I choose, only one that will work is 1. None of the all the rest of them will not work. So this statement is false. False. Spell it right. Alrighty. Okay. There exists an X. There exists an Y. So now I can choose an X, say 2, and now make my Y, the particular Y I choose is 2, that will make this whole. Okay, so there are pairs, and of course 0 doesn't work, but it's okay, because as long as I have 1 that works for each, then I'm good, because there exists as at least 1. So this statement is true. So here are the truth values for these statements. This table here will help you to see when a statement will be true or false. Okay, so when I have both for alls, that means for the statement to be true, any pair XY must work. Okay, if there is a pair of XY that doesn't work, the statement is false. I'm not going to go through this whole chart, but you can read through it similarly, okay, to see each of these to know when the statement will be true and when the statement will be false. Let's look at these 2 examples, and our goal is to translate these statements back into English. Okay, so if we read this statement here for all X, okay, we have C of X, or there exists a Y such that C of Y and F of XY. Okay, now what do all these predicates mean? So C of X is going to be X has a computer. F of XY says that X and Y are friends, and the domain for both X and Y are all students at your school. So we're going to translate this first exactly how it reads, and then we'll think about how would we really say that in English. Okay? And so for all X, since we're talking about X at our school, every student X in your school, okay, is the X, C of X, X has a computer, or there is a student Y such that Y has a computer and X and Y are friends. So I'll say that again. Every student X in your school, for every student X in your school, X has a computer, or there is a student Y, there exists a student Y such that Y has a computer and X and Y are friends. Now, we don't say that in English. In English, how would we sum that up? Okay. In English, this statement would mean every student in your school has a computer or has a friend who has a computer. Okay? And so in English, either statement is correct, but we generally wouldn't say the statement that I read earlier first. Okay? Let's translate this statement here. Okay? Same universe, same X and Y, but now Z is also a student. Okay, so Z is also in our universe. So there exists an X for all Y and for all Z, okay, such that F of XY and F of XZ and Y is not equal to Z. If this, then not F of YZ. Okay, since this is an implication, this is an if then. Okay, so let's read this. Okay, so there is a student X, okay, that for all students Y and Z, okay, X and Y are friends, and X and Z are friends, and Y and Z are not the same person. Are we clear? If X and Y are friends, and X and Z are friends, and X and Z are not the same person, then it is not the case, or Y and Z are not friends. What is that saying in English? There is a student for which none of whose friends are also friends with each other. Okay, so this is generally not a statement. This is probably not a true statement because we talk about the 6 degrees of separation. Everybody has some kind of connection. But this statement is saying there is a student for which none of whose friends are also friends with each other. So now let's translate this English statement into predicate logic, right? It says translate the sum of two positive integers is always positive. And this is a true statement. We know this, the sum of two positive integers is always positive. So it's always easy to rewrite this statement thinking about the quantifiers and the implied quantifiers in the explicit domain. So in doing so, how can we rewrite this statement? For every two integers, if these integers are both positive, then the sum of these integers is positive. Okay? So for every two integers, if these two integers are positive, then the sum of these two integers is also positive. Now, let's introduce variables x and y for our domain. We're going to let our domain just consist of all integers. And if we replace this statement with our variables x and y, now we have for all positive integers x and y, x plus y is positive. So how would we write this statement? Okay, so writing this statement, okay, for all x, for all y, okay, what do we want? If x and y are both positive, so we want x positive and we want y positive, then x plus y is also going to be positive. Okay, so for all x for all y, we first want x and y to be positive. Then x plus y is positive. Okay, and this is the domain, all integers, Is there another way that we can write this a little simpler? Okay. Yes, there is. Okay. And how would we do that? So let's clear what we have here. Okay. And so to do this, we need to change our universe. What if we make our universe just all positive integers? If I already make my universe all positive integers, this will simplify my statement to for all x, for all y, x plus y is, y is greater than 0. Okay? So keep in mind, there's not a unique way to do it, but it's all based on how we have chosen our universe. I want you guys to work on this problem independently, okay? We want you to use quantifiers. There is a woman who has taken a flight on every airline in the world. So to keep it consistent, I do want everybody to use these different predicates in this domain. So P of WF is W has taken F, Q of FA is F is a flight on A, and the domain will be of W is all women, the domain of F is all flights, and the domain of A is all airlines. Okay. Notice here we use them to make it W woman, F flights, and A airlines to make it simple for us to know what we're expressing. Okay. Try to do this on your own and then look back at your notes to see if you indeed get this solution here. Okay. Let's look at these examples and go through them. Okay? And so we're going to use, it says that we want to choose obvious predicates so that help us with the predicate logic. So we're going to choose these here. B of x, y are x and y are brothers. S of x, y, x and y are siblings. And L of x, y is x loves y. Okay? So brothers are siblings. Okay? So since we're talking about, and let's just our universe be all people. Okay? Brothers are siblings. Okay? So, for all x and for all y, okay, if x and y are brothers, then x and y are siblings. Okay? So this is brothers are siblings. Okay? Siblinghood is symmetric. What does that mean in English? That means that if X is a sibling of Y, then Y is a sibling of X. Okay? And so exactly that, we're going to say for all X, for all Y. Okay? If X is a sibling of Y, then Y is a sibling of X. All right? That just means that symmetric, brothers have to be brothers, or siblings have to be siblings. Our next one is everyone loves somebody. So if everyone, for all X, there is someone, there exists a Y, okay? And then we write LXY, okay? Because X is loving that Y. The next one says there is someone who is loved by everyone, okay? So since the someone is the someone that's being loved, and X loves Y, then we're going to start with there exists a Y, that for all X, L, X, Y. Okay, so again, the person that's being loved is the Y. So someone is being loved by everyone. The everyone, X is the one doing the loving. So there exists an X, that for all X, L, X, Y. There is someone who loves someone. Okay, so if someone loves someone, there exists someone who loves someone. So this is there exists an X, there exists a Y, L, X, Y. Everyone loves himself. Okay, so how will we do everyone loves himself? Let's think about that. Okay, so for all X, L, X, X. Because X is loving themselves. Okay? Let's look at, so here are the solutions. Let's look at this last one again, because some folks might have thought of it differently. You say, hey, but my predicates are X and Y. Could I have written this for all X, for all Y? If I do this, I can't just say LXY. That just means everybody loves everybody, right? So if everyone loves himself, I can do L of XY, okay, and X equals Y, which means that X is Y, so you're loving yourself. But you have to include both of these if you're using both predicates. Okay, let's go back to examples. We're going to talk about negating nested quantifiers. Okay, so let's go back to the example that you guys worked on your own. And the example was that there exists a woman that has taken a flight on every airline in the world. Okay, so if you go through the process, you should have gotten this statement here, which says there exists a woman that for all airlines, there is a flight for which the woman has taken a flight and the flight is on a particular airline. So this was the solution for the example a couple of slides ago. What if we want to negate this statement? Okay, there does not exist a woman who has taken a flight on every airline in the world. Okay, so how do we negate this statement? We do exactly that. We negate the statement. We do not of the statement. Right? But if we remember De Morgan's law, our goal is now to let's bring this negation, keep bringing this negation in. And we always want to take the negation as far as possible to the right. Okay? And so in doing so, if we bring the negation over one place, if we recall, then the exist becomes a for all W. And now it's not everything else. That's our De Morgan's law. Okay? Now let's take this negation over one more time. And this for all is going to become a there exists. So we have there exists the W, there exists the A, and now my not is here, and it goes through. Okay? Let's keep bringing that negation over. Every time I bring the negation over one, the quantifier changes. So now we are at there exists a W, there exists a A, that for all X, not of this statement. Now this is our regular De Morgan's law for our and, which says if I bring this in, I apply it to both, and then my and becomes an or. Okay? And so what does my final statement read? My final statement reads, there for all W, there exists an A, that for all X, not P of WF or not Q of FA. Okay, so how do we get to this statement here? Okay, we brought in this negation. So we started with a negation. We brought it in, this changed to a for all. We brought it in again, this changed to there exists. Brought it in again, this changed to a for all. And then used De Morgan's law, this became a not, this became a not, and this became an or. So what does this translate back into English? Okay, that for every woman, okay, there exists an airline that for all flights, this woman has not taken a flight, okay, taken a flight, or the flight is not on that airline. And that is this statement here.